In this world, there are few things as simple as sand on the earth, and possibly none as complicated as computer chips. Nonetheless, the common element silicon in sand serves as a starting point for the fabrication of the integrated circuits that power everything we use today, from quantum computers to smartphones to microwave ovens. Advanced chips can have up to 100 layers, all of which must be aligned on top of one another with nanoscale precision. It is necessary to use different lithography processes for different layers due to the varied sizes of the features imprinted on the chip, relying on the layer used. The EUV or extreme ultraviolet machines, which are the latest generation, are used for the most critical layers with the smallest features, while our DUV, which are deep ultraviolet machines that are the older generation, is used for the less critical layers with larger features. The tiniest particle of dust or other foreign material that gets onto the wafer might cause the microchip to malfunction, which is why chip makers take great care to keep their fabrication facilities clean. How clean is it exactly? The air within the building is approximately 10,000 times cleaner than the air outside. Clean rooms that meet ISO's Class 1 standards are used by the majority of chip makers. This means that there are no more than 10 particles between 100 and 200 nanometer in size per cubic meter of air, and no particles larger than 200 nanometers. A clean, modern hospital, on the other hand, has approximately 10,000 dust particles per cubic meter of space. During the manufacturing process, clean room air is filtered and pumped back continuously, and the staff wears special clothes, often referred to as bunny suits, to assist maintain the air particle-free. Intelligent device manufacturers or IDMs, such as Intel and Samsung, develop and produce semiconductors on a single production line. Foundries, on the other hand, are businesses that make chips for other businesses on a contract basis. This type of chip maker includes companies such as TSMC, Global Foundries, and UMC. The third sort of chip maker is the fabless semiconductor business, which includes companies such as Qualcomm, NVIDIA, and AMD, who bypass the enormous expenditures of constructing and maintaining manufacturing facilities by concentrating solely on chip design instead. These businesses may choose to outsource their manufacturing to a foundry. Silicon chips are now found almost everywhere. Intel develops silicon products that are both industry-leading and world-first. These Intel chips are some of the most complicated devices ever created, necessitating the use of cutting-edge manufacturing technologies to build them. Walk inside the doors of a modern fab where Intel manufactures its chips, and you'll see a variety of sophisticated processes taking up over 1 million square feet of floor area. Chips from Intel are used in ultrabook devices, as well as smartphones and tablets, as well as high-performance computing, data centers, and the internet. They automate industries and are incorporated in autos and other common items, to name a few applications. It is possible for the most complex processor to have hundreds of millions or even billions of transistors, which are connected by fine copper wires. Each of these transistors serves as an on-off switch, allowing the flow of current through the chip to be controlled in order to send, receive, and process various types of data. These days, processors may contain many cores. Silicon, the primary component of beach sand, is a natural semiconductor and the most prevalent element on the planet, second only to oxygen in terms of abundance. The way a chip operates is determined by the design of the chip's transistors and gates, as well as the final use of the semiconductor. Schematics, symbol depictions of the transistors and interconnections that regulate the flow of electricity through a chip, are created based on design parameters that include chip size, number of transistors, testing and production considerations. Designers then create stencil-like patterns out of each layer, which they refer to as masks. In order to do complete simulations and tests of chip operations, designers rely on computer-aided design or CAD workstations to do so. Hundreds of people are required to test, design, and fine-tune a chip before it can be put into mass production. Sand is the starting material for all chips, and it is the most basic of all raw materials. Complicated chemical and physical processes are necessary to produce from sand an ingot of pure monocrystalline silicon, known as a boule, with only one impurity atom for every 10 million silicon atoms, which is then used to fabricate semiconductor devices. The wafers are subsequently sliced from the silicon boules using a unique sewing technique that produces extremely thin wafers. These wafers serve as the fundamental building components for later chip manufacturing operations. It is possible to order them in a variety of different diameters. The most frequently encountered sizes are 150, 200, and 300 millimeters. Chips can be accommodated better on wafers with larger diameters. Silicon is classified as a semiconductor. This indicates that it has the ability to carry electricity while also acting as an insulator. For a wafer to become conductive, small amounts of certain atoms are introduced into the water in the form of impurities. The number of outer electrons on these impurity atoms must be either one more or one less than the number of outer electrons on silicon. The material becomes p-conductive or n-conductive depending on the number of outside electrons in the substance. On top of the p and n-conductive layers that exist on a doped wafer, transistors are constructed. Transistors are the smallest control units of microchips, and they are used to control the operation of the chip. Their primary function is to regulate electric voltages and currents, and they are by far the most significant components in electronic circuits to consider. But how are these layers formed on a wafer in the first place? The layout and design places are the first steps in the process of manufacturing chips from a wafer. Complex chips are constructed from billions of integrated and connected transistors, allowing sophisticated circuits such as microcontrollers and cryptographic chips to be constructed on a semiconductor surface measuring only a few square millimeters in size. The sheer number of items necessitates a lengthy and in-depth engineering process. This comprises defining the chip's operations, replicating its technical and physical qualities, evaluating its functionality, and figuring out the connections between the individual transistors on the device. Before any other process, a non-conductive layer is formed on the surface of the wafer by oxidizing it at a high temperature of around 1000 degrees Celsius in a high-temperature furnace. Then, employing centrifugal force, a photoresist substance is uniformly placed on this non-conductive layer, completing the process. This coating procedure results in the formation of a light-sensitive layer. The wafer is subsequently subjected to light through a photomask in steppers, which are special exposure devices designed specifically for this purpose. The chip pattern's exposed portion is generated, revealing the layer of oxide beneath in it in the process. The component that was not exposed stays in its original state, safeguarding the coating of oxide. Following that, the exposed layer of oxide is etched away in the sections that have been developed using either wet or plasma etching techniques. The wafer is then exposed to light via the mask after the photoresist has been applied a second time. The photoresist that has been exposed is removed once more. The doping process, in which impurity atoms are injected into the exposed silicon, is the next phase in the process. The impure atoms are introduced into the silicon with the use of an ion implanter. The conductivity of the exposed silicon is altered by fractions of a millimeter as a result of this. After the photoresist residue has been removed, a second oxide layer is added to protect the surface. Another cycle of applying a photoresist, exposing the wafer through the mask, and stripping is performed on the wafer. Either contact holes or connector holes are etched into the wafer to offer access to the conductive layers, allowing for the integration of the contacts and interconnections. Once more, the photoresist and mask are applied to the surface. To achieve the smooth finish required for the insulation layer above the interconnections, a chemical-mechanical method is employed to polish away surplus material with micrometer accuracy. When fabricating an integrated circuit, each of these separate stages may be done several times until the integrated circuit is complete. It is expected that the wafer will now hold anywhere from several dozen to thousands of chips depending on the size and type of chip used. Assembly is a final step in the fabrication process. Individual chips are placed in a package and terminals are connected to them in this step. It produces a finalized semiconductor device that can be installed on circuit boards utilizing a variety of different types of connector connections. It is possible to establish over 1,000 connection contacts. For these tiny building blocks to have such a significant impact on our lives, high levels of precision and quality are required at every stage of the workflow, from the manufacturing of silicon boules through clean room production to quality control. This is true today and will continue to be true in the future. Well, that's a wrap for today's video, everybody. Congratulations for making it to the end. If you want to see more interesting videos like this one, do subscribe to the channel and press the bell icon to get VIP access to our videos. Thanks for watching guys, and with that said, I'll see you in the next video. Cheers!